Greetings! We are excited to present our project titled Kiln, Knowledge in an Organic Load and Number. Kiln is a console-based Python program designed specifically to aid in the formulation of ceramic body formulations by calculating the appropriate and accurate proportions of raw materials required to achieve a desired oxide composition. Let me begin by highlighting why this is relevant. In ceramic and chemical engineering, precise and accurate oxide composition isn't just a requirement. It's essential. The mechanical strength, heat resistance, and chemical resistance of a ceramic product are heavily dependent on its oxide composition. Traditionally, ceramic formulation involves trial and error and spreadsheet-based calculations, both of which are time-consuming and prone to inconsistency. Our program takes this challenge by offering a computational alternative that is not only faster, but also gives a more accurate data. Kiln provides a structured and scalable approach to formulation, helping minimize human errors and provides a data-driven solution.
To understand how Kiln works, let's walk through it step by step. First, the user is asked to input the target oxide composition. This refers to the desired weight percentage of oxide like silica, aluminum oxide, and ferric oxide, which are commonly found in ceramic material. Second, the user selects from a list of available raw materials. These raw materials have known oxide contents, which we have already stored in the program database. If needed, the user can even add a new raw material by manually inputting its oxide composition. Once the raw materials are selected, the program constructs a matrix system where each row represents an oxide and each column contains a raw material. This matrix allows us to model the problem mathematically. Next, using numerical Python, NumPy, the program solves this matrix system through methods such as linear algebraic solving, least squares, or pseudo-inverse calculation depending on the matrix structure. The result is a list of proportion of each raw material. These are then normalized to reflect the percentage of each material.
Now, let's delve into the features of the actual Python code. One of the key features of this program is its flexibility. The user isn't limited to using only predefined materials. With the option to input new raw materials, the code can adapt to real-world conditions in certain circumstances in the industry. From a programming perspective, we utilized NumPy to perform high-level matrix operations. This ensures both performance and accuracy. The solver function automatically detects whether the values are squared, underdetermined, or overdetermined, and it selects the appropriate mathematical approach to find the solution. The program also includes error handling to identify issues like negative weight values, which are physically meaningless and can lead to unsolved problems. After computing the weights, the program provides a detailed summary that includes raw weights, normalized percentages, and a side-by-side comparison between target and achieved oxide values. This is critical for validation and helps user immediately identify if their oxide computation will meet their specifications.
For the demonstration, here is a sample execution of Kiln. The program starts by welcoming the user and asking how many oxides they want to match. Suppose we input 6: silica, calcium oxide, phosphorus oxide, aluminum oxide, magnesium oxide, and sodium oxide. We then enter the target percentages for each. Now there is an option to choose whether to add a new material or not. Suppose we choose 2 for this example, meaning there is no new material added. Next, the program displays a formatted table of raw materials showing the oxide content for each. Suppose we select kaolin, talc, and hydroxyapatite. The matrix is constructed with these materials and oxides. The solution is calculated. The program prints out both the raw weights and normalized percentages. In this example, it will tell us to use 28.1% of kaolin, 24.8% of talc, and 47.1% of hydroxyapatite. It also shows a comparison between target and achieved values, which is displayed through its difference. Here is an example of choosing to add a new material. Suppose to enter 1. Yes, add a new raw material. The program asks the user to provide necessary information for it to add the new raw material in the database. The final output gives a sentence-style summary which makes the data more accessible to every individual using the program. That is all for the demonstration of the program.
Kiln holds a significant value for both academic and professional settings. In academic settings, Kiln is a teaching aid. It helps students visualize the direct relationship between raw materials and oxide composition. Rather than manually calculating and recalculating materials, students can focus on understanding material behavior and formulation. In professional settings, Kiln supports faster and more consistent results. It minimizes waste by preventing raw composition and promotes better compositional control. This is value in ceramics such as dental, electronic, biomedical ceramics, and many more.
In conclusion, our program Kiln serves as both an educational tool and practical engineering tool.
By incorporating stoichiometry, material science, and Python programming,
We created something that improves accuracy, reduces formulation time,
And improves the user's understanding of ceramic composition.